All right, we're going to do a couple more examples with setting up integrals in spherical coordinates. And the first one is going to be trying to find the mass of this object here shown on the right, where I've taken an entire sphere, radius 3, and then removed a top cone. And it may also be a little bit easier to see what this looks like in GeoGebra if we could move things around. So let's just go to that really briefly. This is what the object looks like. You can look down into it. And so I'd like to know the mass of this object, given that the density is proportional at any given point to the distance from that point to the origin. So take a minute, put it on pause, and see if you can set up for me a triple integral in spherical coordinates that will give us this mass. All right, so first, if we have, let's call this whole object, this whole region and its interior E. And if we're looking for the mass over a three-dimensional object, we're going to get the triple integral over E of the density. And we can write the density in this case. It's proportional to the distance, so let's let the proportionality constant be K. And then the distance from a point xyz to the origin is just x squared plus y squared plus z squared square root. And now let's switch to spherical to set this up, because the region is cut from a sphere. And also, if we had tried not to do this in spherical, it would take quite a few triple integrals, just because I'm entering and exiting. If I was trying to do it like in Cartesian or even in cylindrical, and I'm shooting an arrow parallel to the z-axis, I'm going to enter and exit along different surfaces depending on where I shoot the arrow. So spherical is really a natural choice for this if I only want to have to use one triple integral. Okay, so let's start with the integrand. In spherical, this is going to become k times rho, because rho is just square root of x squared plus y squared plus z squared. And then I'm also going to need the Jacobian. So rho squared sine phi, and then d rho d phi d theta to give me my volume element. So that's this dv piece here. And then let's think of some bounds. So let's start with our rho bounds first. And I'm going to recommend, when you're doing spherical coordinates, if you have symmetry in your region, if you were able to slice along the ZR plane and you have symmetry, then I recommend that you take a little ZR slice and sketch it. And so here's what I mean about, like, here's a ZR plane where R just comes radially outward. If my theta, let's say, is pi over 2, then this little Z R would actually just be the same as the ZY intercept, or the ZY plane. And so I always just look kind of flat back at my picture on the ZY plane, and I sketch what appears to be the trace, or the cross section. So you can see that cross section pretty easily just looking right back at this page. It looks right like that. That's just the ZY cross section. And it will be that same cross section for any R, right? As I move this around in theta and move this radially outward. And so I'm just going to sketch a ZR cross section. And then you can imagine we get this whole 3D object by now rotating this region around the z-axis. And you may be wondering, why is she using R? Because we're putting things into spherical, but it's because this is a really nice way to slice something that has this symmetry about the z-axis, and it's going to really help as you're setting up your bounds. So I recommend doing it when possible. Okay. And now that's going to help us picture shooting an arrow radially outward, because sometimes in 3D it's hard to picture. I'm starting at the origin and I'm shooting an arrow radially outward in the rho direction. And so on my picture, it's kind of like, I'm trying to show that. And I want to look at where it enters. Well, it's entering the region when rho is 0. And it's exiting, no matter where I shoot this, it's always exiting along, along the sphere, which is the equation rho is equal to 3. And so sometimes it helps actually to label these pictures or these slices, but you can do either way. Okay. So like this is one slice of where rho is equal to 3. Okay. Now let's think about phi. And this is really where doing this ZR cross section helps, because phi is this angle in the ZR plane. And so I need to know where phi starts and where it ends. And so you imagine as you're letting these little red arrows sweep their way down over this region, I want to know what's the smallest phi, which would occur right there. And we can see the largest phi is going to be phi is equal to pi. So let's put that here, because that's going all the way down, giving us this little arrow. Okay, but now I'd like to find this one, this phi, and I can do that by coming up with the equation for, I can do it in 2 ways, but it's easiest if you come up with the equation for this line here, and that's really what we're given. We know that z, this cone is formed by z is equal to square root of 1/3 x squared plus y squared. And so in the ZR plane, this line is going to be z is the square root of 1/3 r, because x squared plus y squared, square root of 1/3 r squared, sorry, is x squared plus y squared is r squared. And we could simplify that. That means that z is 1 over square root of 3r. And so now we have 2 ways that we can find this phi angle. One of them is we could just make a triangle using trig. And so let's start with that. And we notice that if this is our line and this is our slope, this means my rise over my run is 1 over square root of 3. So this has to be the rise, and this is the run. So that rise over run, my slope, is 1 over square root of 3. And then that's going to tell me, just filling in that triangle, that this angle right here has to be pi over 3. Now, if you're not so great at your trig triangles, which is fine, let me show you another way you could get what that angle is. The other way you can get it is take the line z is equal to 1 over square root of 3r and convert it now to spherical. So in spherical, z is rho cosine phi, and r, as you remember, is rho sine phi. And if you're thinking, no, I don't remember this, this is coming back from this picture here, where this is r and this is z. Okay, so set those two equal to each other, and we can, the rows, we can assume rho is non-zero, and so you can divide through by both of those, and this is going to tell me that square root of 3 is equal to tangent of phi. And that's going to tell me that phi has to be pi over 3. So that's the other way that you can do it to get that bound. Okay, and then lastly, because we're going to take this little green slice in this picture here and rotate it around the z-axis for all theta in order to trace out this entire 3D shape, then my theta is just going from 0 to 2 pi. And so putting this all together, or leaving it like this, if you were to actually do this triple integral, we would be able to find the mass. Okay, now let's do one last one. And now I'm going to give you an integral to start, and it's in Cartesian, and I would like you to convert it to spherical. So again, put this on pause for a minute. You will need to be able to picture what this region looks like in 3D, and you'll especially need to be able to picture what the shadow of the region looks like so that you can then translate this into spherical. So put it on pause and then give it your best shot. You don't need to actually integrate, just convert it. Okay, so first thing we need to do is even be able to picture what this looks like. And also we can translate the integrand pretty easily. So that's what I did first, converting the integrand. And then we're gonna sketch the 3D region of integration. So using the lower limits, we can see here z enters along square root of x squared plus y squared. That's a top cone. And then z exits along this, which is actually a hemisphere. And so we can zoom this out a little bit and start to sketch what happens if you were to enter a region along a cone, we have down here, and exit along a hemisphere. And we did an example like this in example 5, but now we need to look at the shadow. So we need to look at these outer two integrals and come up with what part of this ice cream cone are we integrating over. So the shadow is telling me if I shoot an arrow parallel to the x-axis, anywhere between where y is 0 to 3, so that's what I have in the picture here, that it enters when x is 0 and it exits along x's square root of 9 minus y squared, which is this half circle. And since y is only from 0 to 3, it ends up just being a quarter circle. And so this is the shadow. So you can imagine now that this region that we're going to be integrating over is just this portion of the cone that's sitting there in the sitting above the first quadrant. So it ends up being a quarter of the ice cream cone on the left, just the part that's above the first quadrant. Now we need to convert this to spherical, but now it's going to be basically like what we did in example 5, right? Because we converted an ice cream cone to spherical. We're just going to be a little bit more careful about what our theta bounds go to. So when we go to convert this, okay, so the integrand's easy to convert. And then again, I recommend sketching just a cross section in the ZR plane. And so you can look at any R. If it's easier for you to picture, just let, or any theta, excuse me. If it's easier for you to picture, I just look when theta is pi over 2, and then just sketch basically the ZY plane from the picture. And now I'm gonna shoot my arrow to find rho. I shoot it radially outward, anywhere through the region. And I see it always starts when rho is 0, and it always exits along this top hemisphere, which is rho is equal to square root of 18. And then I'm going to think of phi. So in this case, it would be really helpful to see exactly, oh yeah, you can see this here, since I'll label it. Since this line here is z is equal to r, which I get right from this denominator here, then we can see my phi angle, which is coming down from here, is starting at 0 and coming down to pi over 4. And then theta in this case is not going all the way around 0 to 2 pi. I'm only staying in the first quadrant. So theta, which you can't get the theta from this picture, I'm getting the theta from over here where I realize, and basically from my shadow, right, where I realize I'm only going from 0 to pi over 2. Pi over 2. Yep, and then it's all set up. And I could obviously combine my integrand to make it rho to the 4th sine phi, but just wanted you to see where all that's coming from.